right, so let's talk about above-threshold current or the inversion current. So remember, inversion means you have electrons under the gate that are inverted, that are not the majority carriers, they're the minority carriers, but in the transistor they're injected from source and drain. You don't need to generate them. And let's talk about these charges that are in the semiconductor. We have charges flowing under the gate. We can relate the drain current to the charge flowing with a mobility across a certain width of the channel along the channel. Okay? We will overview the few formulas we'll derive in this section. So I'm just sketching them down here. There's something called the square law, which gives you an approximation of the charge in the channel as a function of drain voltage that is falling off the overall potential along the channel. And we would integrate over this charge. There's a bulk charge, which is a more exact expression, and you see it gets to be a little bit lengthy, and it involves a more detailed description of the potential drop in the channel. There's a so-called simplified bulk charge, which now has this coefficient m lumped in to the voltage expression here. And then there's more exact approaches that we don't talk a whole lot in this model or in this course here. Okay, now let's look at the effect of gate bias on the potential distributions in these kind of devices. So here's again the nominal transistor that we're looking at, and we are assuming there is a bulk voltage in the system, and we're going to look at a potential of an electron that is sitting here at this energy level. Okay, oops. And the electron, how would it flow in this potential direction? What would the potential look like? Well, in that direction, it goes from heavy doping N to p doping, and this is just like a p-n junction where we're looking at an electron experiencing a built-in potential from an NP junction, if we're just looking on this segment here, okay? All right. Now, if you're looking for an electron marching in this direction, it also sees an N plus P junction. Now, in a turned around coordinate system, it sees the same kind of potential, because we're assuming this to be perfectly doped in terms of step-like doping. So there's no geometric effects really here. So the potential for landscape for an electron traveling on the green vector looks the same as here on the red vector. Okay? Now, if we consider the gate potential in the structure here, so now we're applying a gate potential here, the potential landscape under the gate looks somewhat different. We're bending the bands down like this, and an electron traveling closer to the gate will see a different electrostatic potential. Okay? So, you've seen this sketch earlier in this section, in the previous section, okay? So the issue is potentials, charge distributions are getting a little bit more complicated. So you just have to walk through it carefully and stare at these images a little bit and get familiar with them. The cool thing is Andy Grove is a co-founder of Intel. He's also a well-known scientist. He wrote a book on semiconductor device physics. The graphs in there are really relevant today still for the fundamental understanding of MOS devices. Okay? He's a fascinating person. Wrote a book, Only the Paranoid Survive, how he really drove Intel to success. So, businessman and fascinating scientist as well. All right. So in this sketch here, I just took the red dash curves from here and laid them over here deeper away from the gate. Whoops. And closer to the gate we have the blue curves, okay? So depending on where you are or where the electron is, it sees a different potential, and us as trying to figure out what is the charge distribution along the channel here, we need to know this is along the channel here, the sketches I just made. We need to resolve that in this direction, and it can be complicated as we apply now an additional voltage between source and drain, okay? So, important. Now, let's begin to apply a voltage. So here's the sketch of the device. Here's the quasi-equilibrium where we have a gate voltage, but we have a built-in surface potential due to the gate voltage, but we don't have a source drain voltage yet. Okay. Here are the bands we sketched before. Now, things get a little bit more complicated as you apply a source drain voltage. Okay, and we'll walk through this diagram in different slices in the next slides. Okay, so the point is, if you had a sheet of plastic or something and you could push down here, you can kind of see how you would bend these bands down, and overall the potential profiles would have to be modified. Sketched in here are also quasi-Fermi levels for electrons and for holes throughout the channel. And those are becoming important for us to calculate electron densities in the system. Okay, so stare this a little carefully. Just in the lecture, I can't do it justice enough. You actually just have to go back and look at the slides a little bit and get your head wrapped around it. Okay, so here we have the quasi-Fermi levels. On the depletion is very different in the source and the drain region, right? Look at, here's the lever arm relatively short compared to here. So this looks, remember when we looked at capacitors, we basically always just looked in sort of in the center, in that region, if you will. We didn't even have source and drain on the left and the right. Now we have an additional landscape that is, or modulation in the landscape that is induced by the source drain voltage. It's like having an MOS capacitor that has a capacitance that is varying in this direction here. Okay, we worried about the capacitance value just at the oxide and at the semiconductor, and had a hard enough time calculating that. Now we need to do this for different spatial regions. Okay, so we'll walk through that. Oh, and the gate voltage here that is being applied must be large enough to make sure we maintain a channel here. Okay, if the gate voltage is not large enough, the channel could collapse as well. All right, so let's look at the effect of a reverse bias at the drain. So let's assume the gates are doped, or you have a PMOS adjacent. So here we go. This is the potential as drawn before with a reverse bias applied. And you can see how complex the gates potentials are bent. And the nice part about this plot is you have these constant potential lines drawn in, or the meshing gives you a feeling, a three-dimensional feeling of how the potential lines will slice. All right, so now let's look at the inversion charge in the channel. Okay, so I drew part of the transistor here. Let's imagine we want to plot the 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 conduction band edge, the valence band edge along the blue arrow that I drew here. Okay, so we're looking at a probe electron that sits here a certain distance away from the gate, and we're plotting the conduction band edge that electron sees. And let's assume we have no gate voltage and no drain voltage applied. Okay, so we're marching with this electron coming from here. We're marching down this vector here and plot the environment that electron sees. Okay, so it sees a conduction band and a valence band that are flat. Now we're going to take a left turn. Coming down, we're going to take a left turn and march towards the p-n junction. Okay, now what that electron sees is a ramp down into the drain. Okay, so that's along this red vector, so to speak. Okay, now this is a plot that tries to visualize the electronic environment in these directional vectors, where we look at band diagrams from the gate into the channel into the drain. Okay, now let's apply a drain voltage. So we're pulling the potential here in the drain down. Okay, we're separating the Fermi levels here, and we have a voltage applied. Okay, so that means the electron sees a deeper drop. Okay, just like this. So far, so good. So right now we assume that the body potential remained constant, and we lowered the potential in the n+ region. Now, let's apply a gate voltage. So now we're adding a voltage here to the gate. What does that do? Well, the gate wants to create a channel, just like what we discussed right under here. It's going to create a notch of a potential in this blue direction. That's this notch. Okay, so that's where it wants to create a channel. Okay, so now we have a drain voltage applied and a gate voltage applied, and we're marching along the blue and the red vector. Okay, so you kind of get a feeling how complicated the potential will be. So the drain bias provides an additional voltage, and the gate voltage is needed to really create an additional channel. Okay, and that has to happen throughout the channel. It has to happen here, 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 and here, and here. And you can imagine that the effect of the drain voltage is more dominant here towards the drain end than on the source end. Okay, so you have a spatial modulation of this notch and the distribution of Fermi levels in the channel. Okay, so you can imagine that the depletion region that you have in the system is now spatially varying. Okay, so you could argue that there is a region that is getting thicker and thicker in which you deplete the charges, or you make the channel thicker and thicker. Okay, so here we're talking about the inversion charge in the channel, and you basically make the effect of the channel different. All right, so let's look at the inversion charge at one point in the channel. So we have both here on the left we have zero drain voltage, but we do have a gate voltage applied, so there is a difference between these two quasi-Fermi levels. And we had calculated the depletion region charge, or the depletion charge in that region in the capacitor calculation. Okay. Now, if we apply an additional bias to the drain, we start to separate the potential here, and we have to increase the gate potential here as well to have the same kind of charge in the system. Okay. All right, so those are on the same level. We can calculate an effective threshold voltage that is now dependent on the distribution of the charge width, or the threshold spatial width in our capacitor. Okay, and that depends on the drain voltage. So we can rescale that into some effective threshold voltage that is now influenced not only by the gate voltage, but also by the drain voltage. All right, so let's see if we can approximate get some expressions here for this charge in the channel. Okay, so I'm taking these two expressions for the V threshold star that is modified due to the gate drain voltage that was applied to the system. Let me plug that in and expand this out. Okay. Previously, we have calculated widths of these inversion layers, right? And they were functions of applied voltages. We have expressions for those, and here are those expressions. Okay, so we just plug those in. They kind of get longer, but again, you see the square root dependencies on voltages, and we're folding in the 2 phi b, just like what we did in the MOS capacitor expressions, and we have now corrections along the channel like that. Okay, so we can derive further approximations to this that make our life at first a little easier. First of all, you could say, well, let me roughly forget about these 2 square roots. They roughly cancel out. That's called a square law approximation. And you can also say, well, I'm going to keep some dependence on these series capacitors in it, and I fold in this factor M. That's called a simplified bulk charge approximation. And we'll get to the difference between those in the next few slides. All right, so here is the sketch of the MOSFET again. And we now are dealing with different Fermi levels and quasi-Fermi levels in the structure. And we'll take a couple of different slices throughout the device. All right, so here at the source gate entry, we have the 2 different quasi-Fermi levels to be the Fermi level of the source. At the tail end here, close to the drain, the electron and the whole quasi-Fermi levels are separated by the drain voltage that is applied, scaled by the factor of Q, of course. And in the region of the channel here, Fn, the Fermi level of the electrons, the quasi-Fermi level of the electrons, will have to drop down from a high level to a lower level. Okay, so it's the reverse bias increase from source to drain. What does that mean? Well, we will now have a variation of channel width in the device. So as I stated, the potential here on the drain side is very large. That makes the channel have a distribution of its width, and in the gradual channel approximation, you will show this in a couple of steps, but ultimately it's of course a smooth function, and you assume that the field in the channel direction is smaller than the field that is in the vertical direction. Okay? All right. So let's sketch these potentials again, as we did at the entrance of the channel and roughly the middle of the channel and the tail end of the channel. So you've separated, this is the drain voltage effectively, you've separated the quasi-Fermi levels for the electrons here in the channel versus the overall drain. Okay, So the voltage and hence the inversion charge vary spatially, okay? So the inversion charge needs to be accounted for. That means this voltage that we have, that we apply in our charge model to calculate the charge is now spatially varying as a function of y, okay? Y is the direction along the channel. So let's plug in some sketches of numbers that we had calculated. So if we just had a normal semiconductor where we have defined a quasi-Fermi level for the electrons and for the holes, and if we assume that the Fermi level here is close to the valence band, we basically have holes, okay? So just like what we've calculated throughout this course, this term will be dominant, okay? And of course, in equilibrium, the product is if Fn equals Fp, then the product is just n times p is ni squared, right? So nothing new really here. Now, if we, by applied voltages, get the Fermi levels closer to the conduction band, we will begin to pile in charge. And we've done this through gate voltage, right? So we effectively pushed the electrostatic potential down such that we have the Fermi level for electrons closer to the conduction band edge. That means we now have significant charge on the electron side in quasi-equilibrium because we have a quasi-Fermi level. Now, if we, by drain voltage, push the Fermi level away for the electrons, we will reduce the electron charge. And if we do this sort of spatially here depicted in steps, we have different charge distributions throughout the channel, okay? And if we then put that together for the whole device, we can see that we will have significant electron density more to the source, and it's decreasing towards the drain due to the modification of the drain potential in the area closer to the channel. So you can argue that the drain is beginning to squeeze the channel tighter and tighter, okay? And you have a charge distribution that is, again, varying spatially, okay? Now, let's look at the depletion into the channel. I just talked about so far about the electron channel. So now let's look at the depletion regions that are under the channel. So same discussion. We have now looking at the gate potential. As sketched here, the gate has pushed the conduction in the valence band down, and that means we must have exposed acceptors, but we also induced electrons. And this is the WT at zero drain voltage. Now we're separating the electron and the whole Fermi level further due to the drain voltage. That means we're reducing the electron charge, like what I discussed previously. And if we push it so hard that ultimately at very high drain voltages and higher gate voltages, the whole density is, the whole Fermi level is above the conduction band edge, we're modifying the electron density again further, because we pushed the conduction band edge again closer to this Fermi level. Okay? So putting all of this together means that our channel is getting narrower, and the depletion region is also getting wider. And that is what I was alluding to in the earlier slides. The effect of the gate of the drain voltage, it modifies the depletion significantly in this direction, because you have a strong effect of exposing the acceptors, and it's somewhat counteracted by the channel getting narrower and narrower due to the interaction of the gate potential with the drain potential. Okay? So you have to account for those different charge distributions. So this is the depletion. Here's another view on these potentials, Fermi levels, as multiple slices throughout the device. So let's, again, we start out with source and on the left, drain on the right, p-doped body. So sliced at the source, it just looks like a p-n junction, just like what we had done before. Now, if you're close to the source, it looks like this MOS cap we had looked at before. If you're further away, you're beginning to separate the quasi-level for the electrons and for the holes, and the potential starts to look like this. If you're much further away, you're driving the system harder, where you have the Fermi level way up here, and for the holes and the electron stays pegged here, and your channel gets effectively, the electron channel gets a little narrower, but the effect, you will have an effect on the exposed acceptors. And here you're separating more and more the Fermi level for the electrons and for the holes as you go down the channel. And if you're far away again from the channel, and if you're just looking down under the drain, it looks like a normal p-n junction again. Okay? All right. So we have a charge distribution throughout the channel. Let's see if we can do some calculation of that charge and see how far we can get. So we can, number one, let's start out. We have somewhat of an expression that we had written down on the previous slide of the charge that is sitting under the gate, but now it's a function of position because of this term here. And now let's calculate chunks of current flow, so to speak, right? We know that current is proportional to the charge times mobility times the electric field we have. And so if we know what, say, a chunk of charge is here, we can calculate the differential of the potential, which is our electric field that will drive the charge through a mobility. And we can do this in multiple slices, slice 1, 2, 3, and 4, slice 1, 2, 3, and 4. And we have the charges, and we have a potential distribution. Okay? So in order to get the total current, well, number one, the current is constant. Okay? So you can pull the constant out of this sum. And let's assume for now that the mobility is constant. We can pull that out. So we're just integrating lengthwise across the channel. So nothing sophisticated here. And if we do this right, we multiply here by the dy to effectively integrate over the drain voltage this expression. Okay? Now, we can integrate up this linear graph very easily as a function of applied drain voltage, and we basically come up with a square expression as a function of drain voltage. Okay, so integrate this expression here with dV up to drain voltage, you end up with a linear term and a square term. Okay, so here we are. We have an expression for the current. Current density, we can multiply by the width of the transistors to get a current. So this is often done here. And you could plot this expression, okay? And it's a parabola, an upside down parabola. So it grows parabolic and it reaches a certain plateau, and then the parabola turns back down. Now, is this physically reasonable that the current turns back down? Not really. So these are unphysical branches of this expression, and we'll talk a bit about in a sketch next why this is unphysical. But basically, you're applying a voltage. The current is not going to stop the channel is going to persist. But this expression here describes well the rise of the current. And we can calculate the top of the parabola where we reach saturation. And so you can just set the first differential to 0, find the peak, and find an expression for the voltage that saturates the current. Okay? And that curve lies on this, results in currents that lie in the parabola. So we can take this saturation velocity, plug it back in here, and get a saturation current. Okay? And that's expression is here, and that's where the, in this description of electron flow in the system, this is where you reach a point where this is the maximum current you can push through the system. So this is the saturation current that stays flat from here onwards, okay? And that saturation current rises up as a function of gate voltage, okay? So here, so you can, given a certain source drain voltage, you basically ramp up the current as a square of the gate voltage. Okay. Down here in the turn-on region, the drain current goes linearly as the drain voltage. Okay, so this is a linear behavior down here. All right. Why does the current become invalid? Well, once you have carriers injected here and they're on a down ramp going down the potential, they will make it down there. So the electrons traveling from the left and the right are swept into the drain under the effects of the reverse applied bias. So they're swept down similar to a BJT as what we had shown there as well. Okay, so once you're in the channel and you're going down, there's really no way back out and back up. So that's why this, this branch of the expression here really becomes invalid. Okay, so if we look at the linear region, in the turn-on region here that I had mentioned before, and expand it out there as a function of gate source voltage, you can calculate a series resistance, okay? So here's the expression for the drain voltage. If you look into the linear region, which is just this term, you can derive a channel resistance effectively. That depends on the mobility and it depends on the length of the channel. Okay, kind of makes sense that your resistance of the channel, your channel resistance goes up as the length of a channel. It goes down with mobility going up. And there's a capacitance in here that's kind of describing the width of the channel, if you will. How many carriers can you get into the channel, right? And it goes as W, the wider you make your transistor, the more current you will have flowing, right? Now, if you, in this expression, you have an intersect with VT, that's your threshold voltage. That's how you start to turn on your device from depletion into inversion. So down here you have the sub-threshold conduction, and in reality, of course, this is smoother. It's not just a ramp-like feature. And the slope gives the mobility. Good. You will have mobility degradation at high gate source voltages. Okay, so here we are. We discussed the above threshold current, the inversion current. We have seen how the current saturates in our square law approximation to the channel. Next, we'll look at some other effects like velocity saturation in a simplified theory. So I'll see you then.